So there will be 6 lectures on this topic of Introduction to Quantum Chaos, and let me briefly introduce Professor Lakshminarayan. So Arul received his PhD in 1993 from State University of New York at Stony Brook, and probably worked also on quantum chaos, right? Yeah, also on quantum chaos. Then he was in Physical Research Laboratory till 2003, and he is now in IIT Madras from 2003, while he is now a full professor. And Arul had supervised 7 PhD students and 7 PDFs. He is also fellow of Indian National Science Academy and Indian Academy of Science. And Arul is an expert in many topics including quantum chaos, quantum information theory, many-body physics, random matrix theory, and he will talk about some of them.
Thank you very much, Debyendu, for the introduction, invitation, as well as the honor of being here in this fantastic place, a lovely place with a long and hallowed history. And I'm very proud and happy to be an adjunct faculty here with all distinguished people. So I'm going to talk about a subject that's kind of close to me. So we have to start with classical chaos, certainly. And so I'm going to assume really no background. In case I'm being too basic, you can always tell me, and I can try to speed up things. But so that's a sketchy plan of these lectures. I'm going to talk about, in 2 lectures, I will try to cover the classical chaos aspects of it. And I think it's important, the classical chaos part of it, also from, of course, the point of view of what's going to come in the quantum, in the sense that they might look different, but actually it pays a lot to understand the classical aspects well enough, because then you will see not only what is common in that, but also what makes quantum then unique. So by the way, I'll introduce and I'll deal with mostly concrete models and simple models, actually, which may not be very physically relevant, but at the same time, they are very relevant. They have been used very much in the conceptual understanding of the subject. The next 2 lectures, I'll deal with mostly single particle quantum chaos, some phenomenology as well as description, semi-classical and random matrix theory, a little bit of that. And that forms really the bulk of the subject, which kind of started in the late 80s and had a very intense flowering for some time in the semi-classical community. And I don't have a very broad overview of the subject actually today, because I'm going right down into the nitty-gritty, but maybe I can just say a few things. And the next 2 lectures will be on quantum entanglement and many-body systems, especially entanglement, but probably more broadly quantum information, but actually mostly really to do with entanglement, because it has to do with the kind of states which are characterizing many-body states which are coming out of chaotic systems, could be, potentially. In fact, my entry personally into quantum information was because I wanted to understand quantum chaos, not because I wanted to understand quantum information itself. So this is the first lecture, or, okay, I'm going to start off. I may not be covering the whole thing in the 1.5 hours, but that's the good thing about a 6-lecture series. I can have a kind of open-ended sessions and not be too hassled about it. And I would encourage, I don't know if that's the format of these lectures. Yeah. Oh, you conduct it, meaning intermediate. Yeah. Okay. Yeah, so please feel free to interrupt. And I think they may be more important than the lecture. At least they be as important, if not more. Okay. Yeah, so as I was saying, maybe I did not put it down here, but just to give you a very brief overview of the kind of historical, in some sense, Um, Classical chaos began with the three-body problem in the late 19th century, and that was the gravitational three-body problem. And it was a very famous work of Poincaré, uh, uh, who addressed this problem of the stability. It was called, and that time itself, people uh, knew the advantages of a punchline. So the stability of the solar system. So this was the question, whether the solar system was stable or not. And it's not an easy question because it's an interacting many-body system, gravitational interacting many-body system. And there were the seminal works of several people, especially Weierstrass, and they formulated this. They encouraged this to be formulated as a prize question as to whether the solar system is stable or not. And Poincaré won the prize with a monumental 200-page analysis of this problem, which has to do with perturbations of the two-body Kepler problem, which we study in undergraduate education. So what happens if, for example, the solar system, you have an Earth and Sun system, let's say, and you have a perturbation of Jupiter or maybe the Moon, and whether this is a stable situation of this three-body problem. So that's that was a question, and what Poincaré found was that he was doing a perturbation theory. There is something called the Poincaré-Lindstedt perturbation theory for nonlinear systems, and in fact the interaction is nonlinear because it's gravitation, and he thought that he had shown that actually this perturbation series converged despite having a very critical problem of what are called small denominators. So proving a convergence of this series was critical to showing whether there is a stable orbits or not. However, and this is all part of the well-known story, that some other person pointed out that there was a kind of an assumption made by Poincaré which made this not really correct on the whole. And this led to a flurry of activity by Poincaré himself, who recalled all the copies of the 200-page proof, which was going to be published. I believe he spent more than the prize money in getting back all of these, corrected this, really, 1 year he spent intensely correcting this, and came up with really what we call today chaos. So chaos was not found, it's sort of attributed to the work of meteorologist, physicist Lawrence and MIT in the 1960s, but really chaos was found by Poincaré back then when he was dealing with the small denominator issues, and found that actually they did not converge. And what we will see as we go by in these lectures, he formulated also more precisely, by the way, his last geometric theorem. If you search for the Poincaré's last geometric theorem, he formulated what happens to essentially these resonant tori, where you have these resonances, these small denominators are there. And he found that there was something which was completely bewildering at that point. He could not even describe it. There is a very poetic description of that. And actually, the American mathematician Birkhoff completed this proof of the last geometric theorem of Poincaré. So there is a large gap. I'm not telling the story in some. I'll show you a book where you can read a very entertaining account of this. So really chaos was appreciated by Poincaré at that time. And people who read Poincaré very carefully, including Albert Einstein, were completely aware of this phenomenon, and Einstein was asking critical questions of the formulation of quantum mechanics by Bohr and Sommerfeld in the 1915 or so, where you have the so-called now old quantum mechanics, and Einstein realized that it can't be extended because of the work of Poincaré, the old quantum mechanics. The fact that the new quantum mechanics developed, it had, and the entire Bohr-Sommerfeld theory became a semi-classical theory, then it went out of the consciousness of much of the physics community. There was very important mathematics which came out of this throughout, so it isn't as if there's a break. But of course, physicists have much more important immediate issues to be dealt with, namely the revolutionary theories of quantum mechanics and relativity. And so for a while, till the computers came by and lesser mortals than Poincaré could actually visualize what's happening, it did not come back into our consciousness. And then, of course, the questions were asked in the 1980s about what happens in the quantum regime. This was loosely called quantum chaos, and it still continues to be called that. Certain people, some important contributors to this, like Michael Berry, would prefer to call it quantum chaology, but apart from him, everybody else calls it quantum chaos, as far as I know. And this subject itself grew with very many tentacles in terms of connections to statistical mechanics, of random matrix theory, foundations of statistical mechanics itself, and then later on in the early parts of this century, mostly into many-body physics and appreciations of things like what happens if you have interaction as well as some kind of disorder, the famous many-body localization problem, and so on, where the, I would say the impact of non-integrability really, which is what chaos is just a kind of a common word for that, is an extreme manifestation of non-integrability, came into play. So that's where we are now, and now it seems like it's penetrated a lot of different fields from gravity, quantum condensed matter, of course, and nuclear physics always came with it. The most early developers of this from Wigner on were nuclear physicists. And atomic physicists. So the early experiments were all by atomic physicists, where I'll come to some of that as we go by. But today I'm going to deal with, starting at the beginning, so to speak, I'm going to really deal with 101 kind of physics. So that's my 10 minutes of an overview, if you wish, or very loose overview from Poincaré to now. But of course, this is an absolute miserable cartoon. Yeah. Yes, please. Yes, please. Absolutely, yeah. So when I say 80s, yeah, I'm sorry, yeah, 70s, I would say, late 70s. In fact, 75 and above, you're right. So there were several papers.
That very type of paper was from Indian Institute of Science.
Ah, okay, yeah. Yeah, I see. Yes, so the Berry Tabor paper, then there was a paper by Shirikov, Ford, Israelev, which then turned out to the kicked rotor problem, localization, dynamical localization, and so on, also around the same time. So yes. Any other comment about this? So let me start then, without too much ado. So yeah, so that's the outline, at least of the first few, first lecture. Maybe it will go into the second, because I don't cover slides too efficiently. So I'll first deal with 101 physics of 1 degree of freedom, but there itself I hope to point out some things which are interesting and of relevance later on. And then we'll go into more than one degree of freedom, and deal with the issue of what is an integrable system, because we have to know what is not an integrable system. You have to know what is an integrable system according to Liouville and all. And then I'll talk about the KAM theorem. I already talked about what Poincaré did in terms of the stability of the solar system. So in fact, he did not show then that the solar system was stable, and in fact, neither did KAM later on. KAM stands for Kolmogorov, Arnold, and Moser in the 1950s and 60s. And their theorem essentially showed that it was a statement of stability, that you could have an integrable system like the two-body Kepler problem, very small perturbations will retain stability for almost all orbits. So in a way, that was a statement of stability which Poincaré was looking for. But it comes with so many caveats that nobody believes that this is really a proof that the solar system is stable. If at all there is any proof at this point, just to jump the story, and that's why I would never finish any given set of slides, is the extensive numerical integrations of the solar system, which indicates that most of the objects which are light objects are actually loosely bound and mostly chaotic. So it's not really stable in that sense. And Pluto is the most famous example of that, was demoted from a status of a planet. Okay, and then we'll talk about sensitive dependence on initial conditions, which is what is the kind of a physicist or engineer's definition of chaos. And then I'll go back, kind of regress into much more simpler systems and just deal with one-dimensional discrete maps. And the most famous of them is the logistic map and the doubling map. And then I will end, first of all, with a definition of classical chaos and what are the ingredients that make up this. So, by the way, I've seen this quite delightful book by former director of RRI, N. Kumar. And for beginning students, I would definitely recommend this book. But I also put it in here because the title itself has exactly what I'm going to be talking about, namely deterministic chaos. The important word there, the key word is deterministic. I'm not going to talk about any randomness produced due to some probabilistic event, but it's completely deterministic. You have some set of differential equations or difference equations with fixed parameters. There's no random number generator to be used. In fact, the question is the opposite. We are trying to find out the origins of randomness. Okay, so for almost the entire of my 6 lectures, I'm going to talk about Hamiltonian systems. So the simplest of them are one degree of freedom classical Hamiltonian systems, where we can visualize a phase space to be a plane in which you have the position and momentum along the x and y directions, and it's generated by the single Hamiltonian function h. And those are the equations of motion which we are familiar with. And there are 3 key examples which we deal with in textbooks, and we will deal with here. So the first is a harmonic oscillator. Second is a pendulum, also sometimes called a simple pendulum. And the third is a double well potential. And so first of all, with the harmonic oscillator. So that's just a parabolic potential well here. And I have 3 particles which are starting off with 3 different energies. And they are going to be oscillating back and forth. And that's the phase space picture that I'm going to be plotting, position versus momentum. I've called it x instead of p here. And so you can see the evolution as they're going by. And you can see that there's something completely curious about this, that they're all starting from different positions, but they meet at the same time at the bottom of the well, and then they depart again. And of course, that's because the time period of this simple harmonic oscillator is independent of the amplitude or energy. So this is a very special situation. It's happening because the system is linear. So it's a linear oscillator, and it has this very significant feature. Whereas if we go to a nonlinear system, like the pendulum is a nonlinear system, let's go back. Yeah. So we'll do the same thing, and we see that these three trajectories starting from three different energies do not have that behavior. And in fact, the particle with the smallest energy has the shortest time period, and as this energy is growing, the time period also increases, and the one which is having this energy, which is almost the maximum possible energy, so that you still have an oscillation, is going incredibly slowly. And that's what's happening on the phase space. You can see that the phase space motion also reflects that, and the one which is starting very close to this energy, which corresponds to the separatrix energy, where a pendulum is transiting from rotations to librations or whatever, librations, what's it called? Complete rotations, librations to rotations, is very close to this critical energy, has a very large time period. So the time period is a function of the energy or amplitude in nonlinear systems. And let's see, another nonlinear system, which is a favorite of ours, namely a double well potential. Now, there are three types of trajectories, those which are confined to these wells. Then there is the separatrix energy itself, and this particle here is very close to that energy, and one which is got higher than the separatrix energy. And you can see that here, the time period has a non-monotonic growth, in the sense that the small oscillations, small time periods, the time period grows as the energy increases to the separatrix, and then as this energy exceeds the separatrix energy, the time period is even starting to decrease and will become the fastest as this goes by. So there is the separatrix energy is a critical energy where the time period diverges. So all of these things happen in typical nonlinear systems, and where you have multiple fixed points like this. You have an unstable point and two stable points here, and this unstable point around this separatrix is what's creating this hierarchy of time periods of frequencies. So why is this important? As when we go to two dimensions or 2 degrees of freedom, because of this range of possible frequencies in these systems, whenever you couple two of these systems or you perturb it somehow by forcing it and so on, all the interesting action would start taking place around the separatrix, because that's where you have a range of frequencies. And so if you think in terms of naively the kind of resonance pictures which we have, there is bound to be more resonances possible around here. Okay. So in fact, the time period for the simple pendulum, so let's look at the time period of the pendulum here as a function of this initial angle theta 0, which you're releasing it by. It can go from 0 to 180 degrees of pi, and the time period increases like this from the famous, I've divided by the 2 pi square root of L by G. So it's starting very close to 1, and then it diverges to infinity when the amplitude is tending towards pi. And actually, for fun, I've put here, by the way, there are exact solutions to the both the simple pendulum and the double well are written in terms of Jacobi elliptic functions. And for the students, this is a very interesting set of functions, which if you haven't studied, you should. They're really fascinating. And it's kind of an ill-understood aspect that almost all integrable systems from various levels of sophistications, when they are solvable, somehow involve Jacobi elliptic functions or maybe some other types of elliptic functions. And the period itself is exactly an elliptic integral of the first kind. So we can write down, I've just written down explicitly the time period. The T0 is the 2 pi square root of L by G. The actual time period divided by this is a function of the amplitude through this elliptic integral which is explicitly given here. And it's amusing that there are two approximations to the pendulum period, which you can see here. One is this, and the other is almost exact. This is actually two lines here. And this almost exact is given by this expression, and this not so great one is given by this. Now, if you see standard textbooks, Goldstein and so on, there is if you manage to go to the perturbation chapter, where they do, well, they don't call it Poincaré-Lindstrom, it's actually some canonical perturbation theory. They would derive for you a time period as a function of this angle theta 0, and it would be a very bad approximation. I didn't put it down here, but you would go to very high orders in theta 0 to get something as good as this. So this is it's not a perturbation theory. It comes from this fascinating concept of what's called arithmetical geometric mean of two numbers. I just put it down here so that if you're curious, you can Google it and find out that the time period is exactly given by the arithmetical geometric mean of two numbers, 1, and cosine of the initial angle by 2. And in fact, I believe Gauss first studied elliptic integrals using the arithmetic geometric mean. He showed the connection between arithmetic geometric mean and elliptic integrals. And I suppose even now, fast numerical algorithms to find elliptic integrals comes via finding the arithmetic geometric mean. Okay. Now, why are these systems which I have discussed so far, which are essentially a lot of our classical mechanics 101, why are they simple? Why are they tame? Well, we'll come to that in a minute, but if you go beyond Hamiltonian systems and just look at all possible two-dimensional flows, so this is a two-dimensional flow, Q dot and P dot given by this set of equations, but you could have any function of F and P here, any function of Q and P, and some other function of Q and P here that defines a general two-dimensional flow. What are the possibilities of such two-dimensional flows? This picture completely describes this. So this is a linear stability analysis, possible what happens to linearizations of the flows around fixed points, and this is the Jacobian of the flow or around some fixed point, and you can see that there are only these kind of equilibrium points. One is this thing which looks like a harmonic oscillator, what's called a stable center or elliptic point. One which looks like a pendulum at 180 degrees, that's the unstable or saddle point. And then you have a bunch of things where you have some kind of a dissipation maybe, and then there is a spiraling in. You could have an unstable spiral. You can have nodes coming in, again, stable, unstable. Or you can have some kind of marginal things where, like free motion, where you have these kind of straight lines. But otherwise, you don't have, and by the way, these are local motion around a fixed point or an equilibrium point, but a global phase space in two dimension is basically stitching together most of these kind of motions. So you don't have anything much more than this. And in fact, for Hamiltonian systems, which is really what I'll be concerned with, there are only centers and saddles, not any of these because of conservation of energy. So you have only these two possibilities in two dimensions, apart from free particle like neutral lines of fixed points. Yeah, Sanjeev.
You have this T by T0, right?
Yeah.
The time period for simple harmonic oscillation.
No, approximation here.
Approximation. So why is this M there in the ratio? I didn't understand.
M?
See, there's this M, right? This T by T0, you have this 2 by pi. First line.
Ah, okay, yeah.
Then there is a M there.
Oh,
right?
sorry. That's clearly a typo of some kind.
Okay, it's not the mass.
No,
right?
no.
Yeah, okay. So
No, sorry about that. Yeah. Thanks for the question. Yeah. There is no M there.
And in the next slide, what this tau and delta indicates?
So you take a fixed point and then you find the linear flow around that. So you linearize the flow around that. So you take so the functions like q dot is f, let's say, and p dot is p. It's a linearization of this f and g around the fixed point or equilibrium point. So it's a kind of a harmonic approximation, if you wish. So it's a linear approximation. So tau is the trace of that matrix, the Jacobian matrix. It's a 2 by 2 matrix. Tau is a trace and delta is a determinant, because it's only the eigenvalues of this matrix that matters. So it's only the trace and the determinant that matters.
So why did you put in that this diagram of these two all the different flows?
This, by the way, I've stolen from a colleague, Sujit, in the aeronautics department from IIT Madras. But this is a very standard picture in all textbooks of nonlinear.
What it indicates that the different flows
Yeah.
coming in different tau and delta.
Yeah.
Does it indicate anything?
Yes. So, I mean, it says that, look, for instance, here, if you take the Hamiltonian flows, right? The Hamiltonian flows, I said, can be only centers or saddles. So they come with tau equal to 0. So always the trace will be 0. That's coming from, again, symmetries and, the fact that the area is preserved. Ultimately, it will lead into that. So, that's for that. And all the flows are organized according to this. So you can see that in this tau delta plane of this two-dimensional flow, the local behavior around them is basically governed by this. As long as it is, there are subtleties which I'm not going into, in the sense that you might have sometimes a situation where the linearization does not describe properly the nonlinear flow. Modulo that, this is what 2D flows will look like in the neighborhood of fixed points or equilibrium points. And more globally, like for example, if you take a simple pendulum here, we had this, or let's take this double well potential. So there are these 3 equilibrium points. So in this neighborhood of this equilibrium point, it looks like a saddle, and the neighborhood of these 2, it looks like a center. And as I said, these are the only possibilities for a Hamiltonian system. And the contention is that the full phase space is just a kind of a putting together of these in a globally consistent way. Yeah.
In higher dimensions, for example, you could have
Stable regions?
submanifolds. I'm saying you could have stable regions rather than single stable points.
You mean a continuous set of periodic
yes,
points?
That's right.
Continuous set of periodic points?
In
or
higher
fixed
dimensions,
points?
you can imagine having stable submanifolds, for example. So that in the 2D systems, would that not be a possibility? Then, you have a very different. So if you have isolated stable points, there are simple classifications. But when you have
So the only
subregions,
possibility in 2D flows is this, where you have you'll have a continuous set of fixed points. So like physically, it would be like free motion. Yeah. So these are situations like that. Yeah, you have stable limit cycle, but that's an isolated limit cycle. That's not. This is a linearization around a fixed point. You can have a limit cycle. I'll come to that. Yeah.
Yeah, but I mean, about the fixed point, if you have a fixed region, then that fixed point, I mean, everything is static, so to speak, in that region, right? So you don't have isolated fixed points are different from
yes. So in a 2D flow, the only possibility is you have one-dimensional fixed points, not a region of fixed points. No. So. So in fact, all the possibilities is encoded in this. Yeah.
This point that you are telling, it's from the analysis of the RG equation or simple?
There's no RG or anything. It's just a 2D flow. I don't have to do any RG. RG leads to flows like this. But of course, you don't need to have RG to have a harmonic oscillator.
Also in quantum uniparticle theory, one can find a fixed line. I'll show you.
Yeah. So in fact, the behavior of what happens to 2D flows is encapsulated in this theorem, again back to Poincaré and Poincaré-Bendixson theorem. It effectively states the following. Let me first state this informally. It says that omega limit set, which means that if you start from any point, what are the omega limit set of that particular point is the set of points that it's going to visit asymptotically in time. So that is where it's going to go eventually. That is the omega limit set. So the omega limit set of any trajectory is effectively going to be one of these kinds. It's going to go to a fixed point, or it's going to go to a periodic orbit. It itself could be a periodic orbit, like in the harmonic oscillator case, it's every point is a periodic orbit. Its omega limit set of every point is just a periodic orbit. Or, as Showan mentioned, a limit cycle. Limit cycle is an isolated periodic orbit. So a omega limit set could approach that limit cycle, or it could be a union of these fixed points and finitely many homoclinic or heteroclinic orbits connecting them. I'll explain this in a minute for those who are not familiar with these words, but that is all the complexity which is there in a 2D flow. Either it goes to some attractor which is a fixed point, or it goes to, so by the way, there is this thing about it being enclosed in a particular orbit, so we are not thinking of things going off to infinity. So if the orbit is closed and bounded in a particular region, so you can read all of that, it's effectively going to this. So what exactly are homoclinic and heteroclinic? Again, we can go back to this because this is considered to be a homoclinic orbit because it starts this particular orbit here, this looking like an 8, or actually this part of it on the separatrix, because it's starting arbitrarily close to this equilibrium point. So at minus infinity time, it's starting from there, and at plus infinity, it approaches that. So that's an homoclinic orbit or a homoclinic extension. And here, if you consider these two points to be different equilibrium points, in a pendulum, they are really the same, but if you consider them to be different, then this is an orbit which is connecting two equilibrium points. At the long past, it is close to one, and in the future, it's close to another. So that's an heteroclinic connection. So these are the possibilities that the Poincaré-Bendixson theorem allows for a 2D flow. And the reason why this is working is because of this thing called the Jordan curve theorem, which to a physicist or an engineer looks like a triviality, but apparently is not. So you take any particular curve, which is a simple closed curve in a 2D plane, let's say, you can define an inside and an outside. This is what Jordan curve theorem says. There is an inside and an outside. You can't go from the inside to the outside without intersecting the curve. Now, because 2D flows, there is one thing which is assumed in all of this, spelling of because. So that uniqueness of solutions of differential equations, this is assumed. Given a particular point, you have a unique trajectory which is emanating from that, and the 2D topology is so restrictive that it does not allow for crossing of orbits because of this uniqueness of flows, and the topology is restrictive, and therefore the simplicity of flows in 2 dimensions. Yeah.
We have these 2 harmonic oscillators, right? Basically, when you.
Which one?
No, I'm saying that this tau, which is the trace
Yeah.
of these eigenvalues, because you are doing linear, you are expanding up to linear, right, around something.
In this, but not, I mean, we are not doing anything
no,
linear
not this one.
here.
I'm just going with the previous
Yeah,
one.
okay.
Yeah. So these are two harmonic oscillators, basically, right, in some sense, or 2 harmonic potential, orthogonal harmonic potentials in some sense, no?
It need not be in a, well, it also includes dissipative cases and so on. So it can be a dissipative oscillator, yeah.
it can be a dissipative oscillator.
Yeah.
But when you say this tau is 0, some of the eigenvalues are 0, does it mean one side is a stable potential, another side is an unstable potential?
No.
Because how do you... because finally you have something x double dot in the... because you have a Hamiltonian system, so you have double derivative in time.
Yes.
And you have linear in position, basically, right, around that point.
Yeah.
Right, so it has to be of the form some x perpendicular double dot equal to something times x, which can be positive and negative, and then mx parallel double dot equal to something times this, right? Isn't it true? Like
you're talking specifically about Hamiltonian systems?
Hamiltonian systems.
Yes.
Right?
Yes. So yeah. So okay, let's go back to this first slide here. So now, if you were to do a perturbation around some particular point, right? So you would get actually you would get why the trace is 0 is because you will have two elements, which is basically a derivative of h with respect to q and p.
Yeah.
For the q part, and here derivative of p and q for the p part. That would be the 2 points in that. Do I use the board?
Yeah, yes.
So some delta q dot. Similarly, so the Jacobian matrix has this structure. So this derivative here first. Yeah. So let me just write that as QP, and then second derivative with respect to P. That's here. Second derivative with respect to Q. Second derivative, but with a minus sign, right? There's some minus signs. Minus sign. So the trace is this, and it's vanishing because of that.
Okay.
So there's
you
nothing
don't,
else.
That term, which is QP kind of term, you don't have in the Hamiltonian.
I mean, you have all of those. It's not as if.
I'm saying that, yeah, so these are just, okay.
Yeah. So, ultimately, it has to do with the fact that here the area is preserved. So this would be part of that, because the preservation of area is also precisely coming from this. That's number one. Number two, the kind of implications it would have is that in eigenvalues like around this, so they would be symmetric. The stable and unstable directions, you would have some symmetric rates which are going on there, which need not be the case if this trace is not 0. Okay, and also if it's in the stable situation like this, you have anyway eigenvalues which are coming in complex conjugate pairs with real part 0, so which is ensured by this. Okay, shall we go ahead? All right, so this is the simplicity of the 2D flows, but I should warn you that things are interesting when once you consider the topology which is beyond that of the plane, and in fact very relevant to us is the torus topology. You consider flows on a torus now, and then the Poincaré-Bendixson theorem has a slight caveat in that. On the sphere, it still remains the same, but on the torus, the genus 1, there's one hole there, it allows for an orbit which is neither going to a periodic orbit. So let's go back to this. So it's not going to a fixed point. It is itself not a periodic orbit or approaches a periodic orbit. And it's not going to union of fixed points, blah, blah. Okay, it's possible on the torus, and this is an important example. And that's why I put it down here. First of all, what is a flow on a torus? You have two angles which are making up this torus. Let's say theta 1 and theta 2. And the flow on the torus is theta 1 dot is some function of theta 1, theta 2. And theta 2 dot is some other function of theta 1, theta 2. This describes a flow on a torus. By the way, flows are just smooth vector fields. So it's defining a vector field on the torus. And you have this irrational rotation, which is this very simple theta 1 dot, let's say, is 1. So it's just winding around with a frequency of 1. So you can immediately integrate that out. Theta 1 is equal to time, except that it's on the circle. So you will have to take a modulo 1 here. I've taken modulo 1. You can take modulo 2 pi in the units of 2 pi or 1. And theta 2 dot is square root of 2. So the two frequencies of these two are incommensurate. It's irrational here. And therefore, if you start with any point, you can easily see that this is going to lead to a series of, this is one orbit. Maybe I'm starting from here, and then I come down here. I will end up at this point here because that's the torus unfolded into a square. And then I flow down here, I go up there, and so on. So it just winds around this torus densely and actually uniformly densely. And you can see a visualization of that flow here. So clearly it's not a periodic orbit. It's not approaching a fixed point or a periodic orbit. So it's not in one of the classes of Poincare index.
So how is it different from the 2D flows? Because in the 2D you have like Q and P, right?
Yeah.
Here also you have theta 1.
It's a matter of topology.
And if it's in 1D, from there, the cases where this Hamiltonian you can write as a Poynting energy plus a potential energy.
Yeah.
Always two eigenvalues will be opposite of each other, right? But the diagonal elements will be zero, right? So it will be always stable in 1D systems.
1 degree of freedom systems.
1 degree of freedom with a potential, where you can write Hamiltonian. You can potential part in Q and P you can write it separate. Some H is equal to some H1 of
Why? The simple pendulum, you have an unstable point. Unstable? I mean, you have an unstable point also.
From here, if I have a H, if I write down as a H1 of P plus H2 of Q, and the diagonal terms are zero, that matrix you wrote down.
Yeah. Diagonal terms can be zero, it doesn't matter.
And eigenvalues will be just the lambda square equal to whatever something.
Yeah.
So then this lambda are just plus.
The eigenvalues, the fact that there is one positive eigenvalue is sufficient for, look, if it is stable, both the eigenvalues will have modulus 1. They will be on the complex curve. Yes, indeed. So, okay, let me go back then. Let me go back here. Yeah. So there will exist a stable and what's called an unstable manifold on this. So okay. What Sanjeev is asking is, you have an unstable point here. You're worrying about the eigenvalues, which are in the opposite signs. Yeah. So one of them will be positive, and that will lead to this unstable direction, and the other will be negative and will be in the stable direction.
Then this curve is so.
Which curve?
Next flows, the tau equal to 0 line, you say.
This one.
No, that whole axis.
Yeah, the whole axis.
That's a tau equal to 0 axis.
Right.
That's a trace equal to 0 axis.
Right.
That corresponds to this one.
Can also correspond to that. That corresponds to this. It can also correspond to the stable center.
I see.
That depends on the sign of the determinant.
I see. Okay, so you are either there or here.
Yeah. you're either there or here or at the center, which corresponds to free particles.
So I could not understand one thing which is the torus, theta 1, theta 2 and Q difference what is it?
The difference is that on the plane, a 2D flow on a plane can have only these kind of eventual, forget about things going off to infinity, which is kind of trivial. Then, thanks, he has a tough job. So you can have either some orbit, any orbit. Omega limit set means the eventual fate of that. Okay, it can probably go towards this. Okay, it's eventually going towards that, or maybe it goes to a periodic orbit. Maybe it starts from somewhere here and then it goes off into this. It's kind of a limit cycle. So something which is around here might be approaching this. So this is a limit cycle. Or it can do something slightly more complicated. It can go to something which is like some bunch of fixed points and some homoclinic intersections between them. Okay, so it can do something like that. It can do something like this. That's all that's possible on this. Whereas on the torus, it can wind around, it's still bounded, nothing is there. In a sense, actually, the torus, because of the topology, it has brought infinity inside. There's nothing in this. So it now need not go to it can do these things also. But in addition to that, it has a situation which is important for us, that it keeps winding around infinitely. It's not going to a periodic orbit, it's not a periodic orbit itself, etc.
So, Arul, in the 2D case, if I have X and P oscillating at irrational frequencies, then they will not go to any periodic orbit, right? They will fill up some region.
What do you mean oscillating at?
So if X and P, let's say X oscillates at omega 1 and P oscillates at omega 2, if I have such equations of motion.
What do you mean oscillates? What is, give me concretely.
Well,
are you saying some kind of Lissajous kind of situation?
Yeah, exactly.
Yeah, but that's not a 1D system. That's a 2D.
Ah, okay, I see.
That's a 2 degree of freedom. Lissajous figures famously intersect each other.
Right.
Draw things that are precessing in the two plane,
Yeah.
which are Q and P. As long as I just keep drawing it and it's precessing.
No, but when you
in
say
a way that
precessing, it's no more autonomous. You're imagining a curve which is itself changing, right? You're imagining something like that.
Right, but it's a vector field. I'm just thinking of
So
a vector
is
field.
the vector field stationary? Is my question.
Right,
at
so
a
there is
particular
something else here, right? We're not only looking at the fact that it's a vector field, you have to have some more condition.
No, the only condition is this: x dot is f of x. It does not involve time. If it involves time, it's a different story altogether. That will be
Right, okay.
going to higher
so
dimensions.
maybe that's the whole point, that space filling. The other thing here, of course, is that the fact that you have D to be a compact region, right? It's a closed bounded region which is compact.
Yeah.
So topologically, anything that's trapped in will have to have at least one limit point that could turn out to be on a limit cycle, but there is going to be a limit point for any, curve which is endless curve on it.
Yeah.
So that's already the case. But I guess the point is that the periodicity of the orbit, the fact that it has a fixed point is not surprising given compactness. But the periodicity of the orbit is what is more surprising. And that comes from this fact that x dot is equal to f of x. That I think is
it could be periodic.
No, I mean the possibility that
Yeah. The possibility is that it could be periodic. And there's a third possibility also. And there's no other. That's the important thing. Yeah. Whereas on the torus, there is another, namely this. This is not there on the sphere as well. Okay. So, shall we move on? Yeah, no. maybe talk into that.
Any physical system that would have a torus topology, any 1D physical system?
Sorry?
Any 1D physical system that would have the phase space topology of a torus. I am having difficulty imagining that.
1 degree of freedom Hamiltonian system in which the torus topology is coming.
But that will have these also, like the coupled rotor, as like this.
Well, if it's coupled, then it's not 1D anymore. I suppose you're asking about 1 degree of freedom. Yeah. So the pendulum phase space is a cylinder. It's not a torus. It's a cylinder. This becomes important when we go to 2 degrees of freedom. Okay. But it's a 2-dimensional flow. I just wanted to point out the contrast, and I introduced it for that reason. Okay. Oh, the equations of motion are not time dependent. Of course, the orbit is time dependent. That's true for everything that I'm talking about.
So, your answer is you need coupled, right? To visualize this in physical system.
You need 2 degrees of freedom to visualize this. Yeah. Okay, good. Thank you for the questions. That allows me to make more out of my slides. So, okay, so yeah, so greater than 1 degree of freedom. Right, so now we are moving out of the plane. So now we have n degrees of freedom. Now our phase space is part of this 2n dimensional space. Our phase space is 2n dimensional, consisting of this n canonically conjugate, n momentum and their positions and their canonically conjugate momenta. And again, you have, that's the beauty of the whole Hamiltonian thing, however number of degrees of freedom, one scalar function which is generating all the 2n equations, first order equations, which are of this kind, and these are Hamilton's equations. And the time evolution of any phase space function is given by this, via this Poisson bracket. Yeah. Which one?
No, this x dot equal to f of x. There x you mean just one.
No, sorry, again, this is 2 degrees of freedom. X and y, yeah. So in general, x and y. X belongs to R2. Cut and paste from some mathematics text. All right. So Liouville-Arnold integrability. It states the following, that a system is called Liouville-Arnold integrable if there exists n smooth functions, f1 to fn, and the first one you can take to be the Hamiltonian function itself, such that they are independent. They are functionally independent. So f2 is not f1 square, etc. And to verify that, you just have to find these vectors, these gradients of these scalar functions on phase space, and check whether they are linearly independent. And if they are linearly independent almost everywhere, then they are functionally independent. Okay, so now these are independent as well as they satisfy this kind of strange condition. They are said to be in involution according to the Poisson bracket. Any fi with any fj should be 0 for any of these. Then, that is, in a sense, these vector fields here are orthogonal to each other in a symplectic sense, because this inner product, this Poisson bracket, is basically an inner product with a symplectic inner product, J being the symplectic matrix. So it's kind of an symplectic orthogonality condition. So if these two conditions hold, then you would call such a system to be integrable. So again, let me recapitulate. Here you have 2n degrees of freedom. I'm sorry, n degrees of freedom. You have motion in a 2n dimensional phase space. You can have at most 2n minus 1 constants of motion. At most, because you have a flow which is taking place in a 2n dimensional space. You will be over constrained if you have 2n constants. Now, here, each of these Fi is in a sense a constant of motion because it has to, the Poisson bracket with F1 has to vanish, which is this Hamiltonian. And you see here, any F that Poisson bracket with H vanishes is a constant of motion. So it says that you have these n constants of motion, including the Hamiltonian H. And not only that, these n constants are independent and they have this condition that not only the Poisson bracket with H vanishes, if F2 is considered to be like H, that's also possible. All the others must commute or Poisson bracket must vanish with that H. So this is a condition of Liouville integrability. Yeah. Good question. It is to cover up for a non-trivial phase space in general. For example, we'll come to that. Maybe I'll make that clear. But almost everywhere means that there is sets of measure zero like points or lines, maybe on some large higher dimensional surface, where this need not be true. So measure zero violations. Yeah. Okay. So what does this mean? Well, the consequences, if you have that, are remarkable. It says that for an integrable system with n degrees of freedom, first of all, you have these common level sets, which are these integrals of motion or constants of motion. So if these n functions f have these values c1, c2 to cn, then the motion is restricted to these level sets. And these level sets are n-dimensional tori. So they are topologically generalizations of this two torus which we showed. So it's just a product of n circles. So there are these angles, theta 1 to theta n. They are topologically conjugate, they're topologically equivalent or isomorphic to a torus Tn. And these tori, they foliate the phase space. That means that they cover up the phase space. Every point of this 2n dimensional phase space has a torus of dimension n on that, passing through that point. And the entire phase space is locally a union of such invariant tori. Okay, I'll show you pictures in a minute. And it implies the following. Because of this fact that there exist these tori, there exists a canonical transformation to coordinates where you have these generalized momenta and generalized positions such that the Hamiltonian is only a function of these generalized momenta. And the equations therefore become simple linear equations. I1 dot is 0, these generalized momenta don't change at all, and the angles theta I are changing. Theta I dot is just a constant, and that constant, it can be a function of these generalized momenta. Of course, these are what we call action angle variables if such a thing holds, a la Goldstein or any standard book. So if a system is integrable, n degrees of freedom, it means that there exists a canonical transformation to action angle variables. And the motion is confined to these tori on which the motion is quasi-periodic, like what I showed for a two torus. I showed this thing winding around indefinitely. That is actually the typical motion with constant frequencies which are given by this. So this is the consequence of this, and we can then, in a sense, solve such a system which is integrable if you have these constants of motion. Okay. Very simple system. Two harmonic oscillators that are not even talking to each other, so they are separable harmonic oscillators. Find two constants of motion, very simple again. So these are F1 and F2, they can exist, these two functions. They are just independent energies here. And are there more constants of motion than these two? It is interesting that there can be more than two, and especially in the case when you have omega 1 and omega 2 being rationally related. To see that, define these complex numbers, Q1 plus IP1, Q2 plus IP2, and then these things can be trivially solved in this. By the way, we use harmonic oscillators only when we do quantum mechanics do we introduce sort of complex Q plus IP combinations for the creation and annihilation operators, but actually that's should be done at the level of classical mechanics because.
And it is done actually for diamagnetic problem, for classical diamagnetism.
Okay.
That it is easily.
Okay, very good. But even for harmonic oscillator, it should be done. Because it's just a rotation in this thing here. Okay, so it's a rotation in this proper thing. So then you can eliminate time between these two by just dividing this Z1 by Z2. You see, because then it's a constant of time. Z1 0 divided by Z2 0, and therefore, but that's in general a complex number. The real part and imaginary part. So you can consider this ratio Z1 to the power of omega 2, so that you get this omega 2 here, and then Z2 to the power of omega 1. This will be a constant. It's a complex constant, so you can take real part and imaginary part. But now it looks like there will be 4 constants, F1, F2, real part, imaginary part. Since you guys have been asking me questions, maybe I can pause and ask, especially the students. As I said, this is now 4-dimensional phase space. You cannot have 4 constants of motion. If you did, nothing will move. So you can have at most 3, but it looks like we have 4. What's the resolution? Yeah, what is not independent? Yeah, but you can see that if you take the modulus of this, right, modulus or square of this, then that is that will eliminate for you the so you'll have essentially these combinations here. So the modulus of this is it's only the phase of this f which is giving you this other. But it's very interesting to find out what these constants are when omega 1 by omega 2 is rational or irrational. But again, you see, that's a very peculiar thing that the rationality or irrationality of this matters, because if it is rational, there is a third constant which some of the old classical mechanics book call isolating integral. That means it's really an useful integral. This, if it is this third integral, the third constant which you can find is not very useful if omega 1 by omega 2 is an irrational number. That's because you have some kind of branch singularities, branch points here. And if, for example, omega 1 equals omega 2, that's the simplest isotropic oscillator, right? In the case of an isotropic oscillator, what is a third constant of motion? An obvious kind of physical third constant of motion. If omega 1 is equal to omega 2. If omega 1 equals omega 2, this has got a symmetry of rotation, q1 square plus q2 square, and the symmetry gives rise to angular momentum conservation. So the third constant is an angular momentum. So that comes out immediately if omega 1 equals omega 2. But even if omega 1 by omega 2 is, say, 3 by 2 or 5 by 3, you still have an useful constant. Although it is now breaking the symmetry. It's no more rotationally invariant, so it's not angular momentum, but there is a useful isolating third degree of third constant. Isolating means that in phase space, the trajectories lie on a lower dimensional surface because of this additional constant of motion. But if it is irrational, this is no more the case, and you have only these 2 constants. Okay, so indeed, now the action variables or the generalized momentum variables are given by these. They are already, we know that that's the action variables for each of the separable system, and the Hamiltonian can be written in this way. This is from standard books in the harmonic, in this. So this is just an example which I gave here. A Hamiltonian can be written purely in terms of these actions. This is an example of that. And if omega 1 by omega 2 is a rational number, then this torus, by the way, the torus is now precisely the, yeah, go ahead.
Say there will be minus
is equal to 2.
Yeah.
So the example where 2n minus 1 will be what?
So 2n minus 1 is a maximum
Yeah,
possible.
so I'm saying that maximum degrees of freedom, if I couple them, that will make
Omega 1 equals omega 2 is an example of that. Right? I mean, you have three constants there. Yeah. In fact, when omega 1 by omega 2 is rational, you have a third constant as well. Only thing is, I can't say that is angular momentum. In fact, all systems which have more than n constants, independent, blah, blah, are said to be super integrable, because integrable requires only n constants. See that this is only half of the number of, it's only the number of degrees of freedom, half of the phase space. Anything more is extra. Like, we are very happy that the Kepler problem is super integrable, because thanks to the super integrability of the Kepler problem, we are moving in a closed curve. The Earth is moving in a closed curve. Otherwise, central forces are not sufficient for us to, it's a particular central force of 1 over r square that ensures that you have this additional constants. It's not just lying on a torus, it's lying on a closed curve. Okay, now this, yeah. No. No. Yeah, I mean, you can have closed orbits even without, of course, you can have closed orbits even without integrability. Yeah. It's just that the probability of being on one is very small. Yeah, so now the tori structure should be rather clear, because each one is moving, there is an phase space, there is an angle associated with this. So you can just think about the angle in each of the individual phase spaces, and the product of the angle is the torus that we are talking about. And if omega 1 by omega 2 is rational, you will have closed orbits on this. The tori is filled with continuous families of closed orbits. Maybe a bit like what you were talking about, except that it's not fixed points. They are continuous families of periodic orbits. And these tori can be interchangeably called rational tori, because the frequencies on that are rational number, or resonant tori because, well, it's a condition of resonance. And in general, if you have an n-dimensional torus, a rational torus or a resonant torus condition is that there exist integers kj such that the sigma kj omega j equals 0. Okay, so there should exist some integer, n integers, such that this condition is true. Then you will call that a rational torus. This generalizes beyond 2. And if this is irrational, then it is filled ergodically. That means that any point that you take, initial condition that you take, winds around this continuously, so that it comes arbitrarily close to every other point on this torus. And this tori fill ergodically with any one orbit. Of course, there are infinity of orbits here as well, each of them being ergodic. Such a torus we will refer to as irrational torus, or sometimes non-resonant tori. Now, in the simple examples like this, either the phase space is entirely filled with rational tori or with irrational tori. There is no combination. In general, this is not the case. In general, you will have, so this is a picture of, let's say, the 4-dimensional space. By the way, I'm talking about 4-dimensional phase space, but for a given energy, it's restricted to a 3-dimensional submanifold, because energy is a constant, it's lying on this 3-dimensional submanifold. You can consider all orbits of that given energy. It's still a 3-dimensional space, very large space, and the tori I'm talking about could lie in this 3-dimensional space. So you can actually imagine like in a room in which we are having these tubes which are concentric tubes to each other. You can visualize it like this, and therefore this is a visualization of that. And you have these tori which are now foliating this phase space, and they need not be all rational or irrational. So you could have rational, irrational, rational, irrational, and so on at the same energy. So that's because in general these frequencies are not constants. It goes back to my first slide where I showed the harmonic oscillator having this peculiar property that the frequencies are independent of the amplitude. That's why all of them were meeting at one point. But that's completely pathological. So in general, that will not be the case, and therefore here also these frequencies will depend on the tori. And the tori are described by these constants or these actions, I1 and I2. Each pair of I1 and I2, you can think about it as a radius roughly of the longitude and the latitude or something like that. This in a the circle like this and the circle in the perpendicular direction, roughly speaking. So those will be related to this I1 and I2, and the ratio of these frequencies is not a constant. It will be changing depending on the value of I1 and I2. So the rational and irrational tori foliate intricately. In fact, it's pretty much like the real numbers in the unit interval, where rational and irrational numbers are intermingled. There's no intervals of rational numbers, no intervals of irrational numbers. Same way with these tori in phase space, rational and irrational tori intricately intermixed. Arbitrarily close to an irrational number, you'll find a rational number. Arbitrarily close to an rational tori, you'll find an irrational tori, and the other way around. Life can be interesting. So, very simple example. Let's go beyond the harmonic oscillator. Let's just do quartic oscillator to the power 4. So it's still separable, therefore it's an integrable system according to the definitions of Liouville and Arnold. Energy can be given like it's not a linear function of I1 and I2, it's a nonlinear function, and therefore the frequencies depend on the actions by the simple way here. And therefore these frequencies are changing, and there is an important condition which is called a non-degeneracy condition, which is basically telling you that these frequencies are changing with the actions in such a way that if you give me the actions, I know uniquely the frequencies, and if you give me the frequencies, I know uniquely the actions. This is invertible. This is not the case with the harmonic oscillator and any coupled oscillator, nothing like that.
Q1 minus Q means if you add plus Q1 minus Q2 square, this problem will break down.
Which one? Sorry?
This quartic oscillator.
Yeah.
You have this term plus I add Q1 minus Q2 square.
Q1 minus Q2 squared, yeah.
So could it still be, because it's not no longer separable, right?
Yes.
So in that case, we will not be able to say is it integral.
Most likely it's not integrable. I will use that example. Coupled quartic oscillators. Yeah. Yeah.
Because it's just depending on I1 and I2.
Yeah, but the point is that I1 and I2 are constants of motion on a given, so for a given trajectory. It's not as if it's a universal constant. If you move from here to here to here, it's not a constant. Yeah? Yeah. Okay, so this derivative makes sense. This is a function of these, so you can take the derivative and... So this is a Kolmogorov non-degeneracy condition on this. So now, okay, so this is all the kind of integrable systems that we know. We'll come to non-integrable systems, which is the subject of these lectures. I'm doing very well, 18 by 43. I think I don't need to write any more slides. All right, so these are all the integrable systems, 2 degrees of freedom. 2 degrees of freedom, one more constant, that's all that's needed. All 1 degree of freedom, of course, I'm eliminating that. 2 degrees of freedom, you just need one more constant apart from energy. If it is not separable, usually it's angular momentum, okay, but it need not be, as we saw in, they need not be. Textbook examples, particles restricted to the inside surface of right circular cone, hemisphere, etc., all that we are subjected to in grad school or MSc and so on. All of them are really thankfully integrable to some extent, but it's fun to imagine what you can do to these problems to make them non-integrable. Particle in a rectangular box, integrable, a billiard, I'll come to billiards. Any central force potential, including particle in a circular enclosure, like a billiard, circular, because of the conservation of angular momentum. 3 degrees of freedom, 2 more constants are needed apart from energy. The two-body Kepler problem is the famous example. All components of angular momentum, which is really sufficient, but in addition there is this Runge-Lenz vector, which, as I said, makes the problem super integrable and restricts. Actually, there is a family, continuous family of closed orbits, which is not the case if you don't have this. Okay, and here I'm saying all central force problems. Greater than 3 degrees of freedom, constants are often obscure, well, in my opinion. For example, a Toda chain is a very famous example. Nearest neighbor potential is this exponential Qn minus 1. So these are particles, let's say, in 1D, and nearest neighbor coupling, and the nearest neighbor potential is given by this, is a famous example of an integrable system, any number of particles, n particles. The famous Calogero, Sutherland, Moser models, where the pair potentials are inverse square type, again in one dimension, 1 by Qn minus Qm whole square, etc. Pair, now pairwise, it's a 2 particle interactions, is an integrable system. The famous KdV equation, the Sine-Gordon field or continuum field theories, the nonlinear Schrodinger equations, all of them are integrable in 1 plus 1. So all of them have these, because these are having infinite degrees of freedom, n equals infinity, you have infinite number of constants in involution, and they are independent. So, and as you know, all of them have some kind of soliton solutions and so on. Fascinating history of that, which starts from Fermi, Pasta and Ulam trying to find a non-integrable system, and they find solitons essentially. The whole history of soliton physics begins from there. So all of that is the integrable systems examples, and there are many more. This is what I put on the board. It's a very fascinating topic itself, finding integrable systems and studying them. FPU? No. It's not integrable, but while trying to investigate that, essentially they found that, the continuum limit of that, one of the continuum limits is a KdV equation, which supports solitons. The KdV itself is integrable. So you can have, so there's a whole host of things where you have, let's say, discrete models, which you are making into a field theory. This can actually change the structure of integrability. You can have integrability because you have made it a field theory or continuum theory. Same time, you can take a continuum theory, make it into a discrete theory, and you can break integrability. It's some difficult task to keep integrability if you want to go from an integrable field theory to an integrable discrete model. It exists, I believe, very interesting theories of that kind.
Discrete models.
Yeah, these two are discrete models. Okay, so my next topic is going to be what happens when you perturb integrable systems. So all integrable systems are of this form, like if you have 2 degrees of freedom, there are 2 actions, and the Hamiltonian is like this. You have a perturbation which is now involving not just the actions, but also the angles. And there is this theorem of Kolmogorov, Arnold, and Moser, and it kind of tells you, along with the Poincaré-Birkhoff theorem, what happens in this qualitatively. So I already introduced rational tori and irrational tori. So this is the summary. A rational tori are fragile and they are immediately destroyed. This is essentially the Poincaré's last geometric theorem, which Birkhoff completed, says is fragile. In fact, chaos begins around these rational tori. So rational tori are fragile and get destroyed for however small your perturbation may be. So it's qualitatively different. Irrational tori are robust and they remain, they are only slightly deformed. The good news is because most of the numbers are irrational, most of the tori are irrational in some measure theoretic sense, arbitrarily close to an integrable system, typically you will find still stability and quasi-integrability. But I say typically because there are conditions which are required for the Kolmogorov-Arnold-Moser theorem, which need not be satisfied. For example, harmonic oscillators do not satisfy the conditions of the KAM theorem. And we know harmonic oscillators are very important to us. So here are the pictures of what's happening to these tori. This is a very nice book, Jose and Saleta and Classical Dynamics Contemporary Approach. You can see the cover picture deals with that. These are the tori I'm talking about. Now it's a section of the torus. So it's now a section of this. And so the tori will be just closed curves. And you can see that some of the closed curves remain like this. But intermediate, you can see that there is a whole lot of not tori at all. There is very complicated dynamics in there. And that's all this rational tori which have been destroyed. And there is this very fascinating book called The Camp Story by Scott Dumas, which I highly recommend. This is the cover page from that, which again, we will deal with systems like this in detail in the coming lectures and also deal with the quantum mechanics. But you can see again here clearly, there are tori which seem to remain as tori, and then you have a very interesting kind of resonance structures, then you have chaos kind of forming out there. So these tori are breaking up and all the fun and games begins here. But maybe I should use this as a natural boundary to go tomorrow into this perturbations in more detail. Yeah? Yeah.
Irrational one, it fills up the tori, right?
Yeah.
But like if I take two trajectories, initially they are close by, they remain close by or they diverge?
On the torus.
On the torus?
Yes, they will remain close by.
So there's no...
The motion on these tori remain quasi-periodic.
Quasi-periodic, okay.
So
they don't...
There's no chaos, nothing on these irrational tori.
Okay.
No. All the chaos and this thing you will find only here, in these neighborhoods.
So then for rational tori, you cannot have chaos, or what is the meaning of this?
The resonant tori...
No, irrational, sorry. In irrational tori...
Irrational tori, if you have irrational tori, on the tori there's no chaos.
No, if you
remain on the tori.
I see. Even if you perturb it, there is no...
If you perturb it, meaning...
By this epsilon...
No, but this you already perturbed it and you get the irrational tori. So...
I thought you...
No, so, okay.
Sorry.
Yeah.
I thought you were start with the irrational tori and then you perturb it.
We are starting with... So, when epsilon is 0,
yes,
you have both rational and irrational tori.
Yes.
Okay? So you have a bunch of circles like this, or things which are topologically circles. So they can be rational, irrational, rational, irrational. Okay? Now you turn on this perturbation. The statement is that these irrational tori, they survive and they just distort slightly. Motion on them is still quasi-periodic, like it was. On resonant tori, these don't survive at all. They break up and they lead to chaos. That's the, so the...
I guess that is related to previous explanation of I omega 1, that things which you were studying, like when you were giving this angular momentum example.
I'm not so sure, no.
In this case,
Yeah.
for example, in this case.
Right.
So you were saying for the rational omega 1 by omega 2 rational, in that case you could write I omega 1 plus I omega 2, right?
No, that you can write, no,
So
sorry.
rational means you have
No,
only two,
no.
and in the irrational it could have other one.
No, okay, that is constants of motion, but this is irrespective of whether omega 1, omega 2 is rational. Yeah.
But the constant of motion,
The third constant of motion comes only if it is rational.
rational, right?
Yeah. Yeah, but by the way, I mean, look, this statement that I'm making is very general, does not involve the third constant or anything like that. That involves this combination of rational and irrational tori.
So here you have both rational
and irrational mixed into one phase space at the same energy also. You don't have to go to different energies.
So these tori, all of them, do they have to be concentric always?
They foliate the space, yes.
And can I have like different?
So actually this kind of connects to your question about, you asked why should, where is that condition, almost condition, because imagine something like this. So maybe you have two double wells and then they are starting to interact. Actually it's an interesting problem, probably not well studied. But if you do that, you can imagine that now there are three types of tori, those which are like these, those which are inside, right? And then there are these two tori. And then now they are separated by these points here. So now there is a foliation. If you can just imagine this to be a cross section of a torus. But now you see that now there is this torus family and that torus family don't talk to each other. So they are foliated, they are still foliating, but it's locally you can think about it like this. But always you have some structure which is inside the other. It's an onion-like structure. But you can have some structures like this where these onions are slightly separated onions. And then you can have some larger onion on top. Cross? You mean actually intersect? No. See, these tori are formed by orbits, phase space orbits. The collection of phase space orbits forms these tori. If two tori intersect like that, that would mean there is some intersection of orbits. It will violate uniqueness and so on. Okay, so here it appears in these things as if they are intersecting, but of course that's not intersecting. It's intersecting at an equilibrium point, which itself is an orbit. Okay, yeah. So no, they don't. No such collisions happen unless you put in some time dependence, in which case it's a different ball game. None of these things are stationary. Good, yeah, thanks.
So, what will happen if we start to increase the perturbation strength?
Good question. More chaos, more fun.
So,
But this all feeds into the KAM story. The KAM story, they are mathematicians, they have to control, they have to talk, what they can control. So the perturbation levels which they were able to control were so minuscule that they were not applicable even to, that's why the Jupiter kind of realistic physical systems, they were so small. But practically people found that these statements hold for much larger perturbations. We'll come to that. But again, yeah, it's a complex question. It might depend on the system that you're studying. How much perturbation can you have? Because as you're increasing the perturbation, these irrational tori are not going to be there. I mean, I said that there will be irrational tori. They will be there for some epsilon. As you're increasing the epsilon, they will be increasingly getting broken away. That's the whole story of chaos, actually. And I would say partially understood.
Anybody has any other question?
Anyway, there's much more opportunity, so please digest. Thank you very much. Thanks for all the questions. Thanks for coming.